Okay, guys, so today we'll be going through on complex numbers. So this will be uploaded on my YouTube channel later. So if any of you miss it, y'all can see the video later, right? So complex numbers, in my opinion, I don't actually, it's not necessarily like a conceptually hard chapter, but rather is a very tedious chapter actually, in my opinion, and that it draws on your Sec 3 A math actually, polynomials, your understanding of polynomials and the factor and remainder theorem. It actually comes into play here in complex numbers. So it's something that I realized later on, especially when you have to like factorize out like example, you have to factorize out cubic equations. So you actually have to apply your what's that thing called? I can't remember what's that thing called, but like the like I cannot remember the name suddenly, but like you have to like divide like az cubed plus bz plus c with like a z minus a or something like that, and then you get like the remainder is like some like a polynomial of a power of two. I can't remember what's the name yet. Oh yeah, long division, long division. Yeah, actually it comes from long division. So right now we'll be exploring complex numbers. We'll be doing a crash course. So this will be very, very summarized. It might not go through everything, but it should go through most of the things that we will need for today. So complex numbers, let's start right now officially. So the very, very fundamental thing that everybody should know about complex numbers is that we define the imaginary unit I, right, to be square root of -1. So that's the most important thing that everybody should know. I hope everybody knows that by now. So if we square both sides, right, I squared equals to -1. So these are the two properties that I'll start off with. This forms the entire basis of what complex numbers is about. So in complex numbers, there are three forms that we learn, three ways to express complex numbers. Just like how um, for angular measurement, we have theta and we have theta, my apologies. To represent angle, we have degrees and radians. So we have three forms of representing complex numbers. So the first one is Cartesian. The second one is trigonometric. And the third one is actually polar. So do know that actually the three, right, they mean the same thing, just that it's expressed in different ways. The same thing. It's just so it's like it's like you have three different ways, three different like it's like three different weapons like that. It's like each weapon is for a different purpose. So depending on the question, right, one of the ways is easier than the other. So it's up to you to choose which path you want to go lah. So it's like you have to see which one makes the most sense to use in the question, and then you will just whack with like whatever you think is the correct one lah. So actually all three will end up in the same result. It's just that one is easier than the other, right? So now we go through Cartesian. So Cartesian, right, simply, right, it's just z. So z, we represent z. Z is a complex number. Usually we denote by the letter z. So z equals to x plus I, y. So you can see here, right, there's a real component and then there's an imaginary component. So this is how we denote. Re is real and Im is imaginary. So I is the imaginary unit here, I. So y is a real coefficient actually. So Cartesian. So Cartesian is like the first one, the first form that normally like most schools teach lah. So what does it mean by z equal x plus I y actually? So Cartesian equation, right, it's very visual. I mean, it's in the name, right? Cartesian, like we learn Cartesian coordinates, right? It's the same idea actually. So we represent complex numbers on this thing called an Argand diagram. So this is how you spell it. So Argand diagram, right? So it's like your x and y axis, right? It's like x and y, just that this time we represent it by real and imaginary. So we denote here as the real axis and denote here as the imaginary axis. So for some intuition, right? You can think of it as like, real numbers is like, the number line is like how we learn the number line. It goes from negative infinity to infinity, right? But the thing is that mathematicians notice that you can't exactly represent complex numbers on the real axis. So it's not, it's a bit hard to perceive what square root and -1 is. So what they did is they invented this new axis called the imaginary axis for us to, in a way, to visualize what complex numbers actually mean. So just for some intuition lah. So it's like another axis, it's like another realm that we are exploring into. So these numbers don't actually fit into the real axis so per se. So that's why we create another one so that we can represent them geometrically. So there's some intuition lah. So let's just say we start from 0, right? I have a number, I have a point here, and then it's denoted by x and y. So we can see it's really like, it's similar to like Cartesian coordinates, which is why the name Cartesian came from, I suppose. So let's just say we have z1, and then this is x and y. So here, right, this distance is x, while this distance is y. But here, right, because we have the imaginary axis, right, that's why z equals to x plus iy. So that's how we kind of like visualize what the thing actually means lah, right? So yeah, so nothing much lah to understand, just that you need to realize that these are absolute values, these are magnitudes. These are magnitudes. So just on something that I found interesting is that actually, right, you can OZ, right, itself, right, it's actually kind of like it's kind of like a vector with like x and y, just something random. You might need to use this, I don't know, but like you can represent this as a vector, so starting from 0 to z, so it's like a vector itself. So yeah, with a direction that's, with this is as the direction, since it's uh starting from the origin, right? So Argand diagram helps to represent Cartesian coordinates lah. So that's the first kind of form that we'll go through today. Just a crash course, z equal x plus iy. The coordinates are x and y, just that we add the imaginary unit in front of y so that we can able to represent it on the imaginary axis. Okay, yeah, so now that we go through the first form, now let's go through the second form. So now the second form that we go through is the trigo form. Actually, okay, let's go through all three together, because the exponential form is similar to the trigo form. Actually, the trigo form comes from the exponential form. So right, if we have something like z, so exponential form, let's go through exponential form first. So z, right, can also be represented as r e to the I theta. Yeah, so it might seem a bit like counterintuitive at first. Like, what do you mean by e to the I theta? It's actually quite interesting. I don't actually really know the derivation or like the intuition behind this, but that's how like I learn it. That's how like we learn it at first. So r, right, is the magnitude of the vector z. So actually we can actually think of this as vectors in a way. These are actually kind of like vectors in a way. So that might help with some intuition right there. So r, right, is actually the magnitude of z, which is the magnitude of the vector z actually. So yeah, and then theta, right, is called the argument. So what do you mean by argument? Let's go back to our real and imaginary axis. So this angle that let's just say z makes with the horizontal, right, it's called the argument. Basically it just means the angle with respect to the horizontal, and we always define theta from the positive imaginary axis. So we always start here. So let's just say we have a complex number here, z, right? The argument starts from here and it goes here. So this is the argument of z. So do take note that it must start from the positive, sorry, my bad, imaginary, it must start from the positive real axis. Let me repeat that again. When we define argument, it always starts from the positive real axis. So getting away is like sweeping like that. So likewise, right, if you have a complex number here, right, z, what you do is you don't actually go here, but rather you actually start from here. So in a way, it starts from the real axis, and we look at the smallest angle that it takes to get to that number. So it doesn't matter whether it's negative or positive. So we'll talk about negative and positive arguments later, but just take note that this is the idea of what argument is. So anyways, go back. So right, okay, let's go back. So now that we understand what z and theta is, right? So if you have the modulus of z and you know the argument, you can actually represent it as e to the I theta. So it's quite interesting, e to the I theta. So yeah, and then right, what you want to do, so now that we understand, so the exponential form is essentially like this. So now let me show you the link between the exponential form and the trigo form. So z equals to r e I theta, but it's also equal to r, to take note, cosine theta plus I sine theta. So you can see here, right, this is the trigo form, but the trigo form comes from the exponential form. Or likewise, vice versa, like the trigo form can also help you to define the exponential form. So they're kind of like circular in a way. So r in this case still means the magnitude of the vector z, and then the theta is the argument. And then take note that it's really is by strictly by definition that it's the I belongs to the sine theta, and the cosine theta has no I component. So you can see here, right? If we multiply this in, right? Let me clear up the whiteboard. If we multiply this fully in, right, it becomes z equals to r cosine theta plus r I sine theta. So actually, don't you think this actually looks like the Cartesian form? And it actually is. So right, if you know what theta is, right, and you know what r is, right, you can sub in the values and you'll get back z equals to x plus iy. So the cool thing about complex numbers is that these three forms are actually kind of the same. They really are the same thing. So you can see how like you can just switch from one form to another uh in whichever way you like that helps you solve the question. So something that I really enjoy about complex numbers is how you can like switch around the forms and you can play around with it and you can see which one actually makes the most sense lah. So you can yeah. So actually you can see here, right, this is the real component and this is the imaginary component. Just like how this is the imaginary component and then this is the real component. Okay, yeah, so that's the three forms. So actually, honestly, that covers like at least like 25% of complex numbers already. Okay, so now let's go through arguments. Let's have some understanding of what arguments really mean lah. So okay, so let's go back to our analysis of the argon diagram here, right? So we have the real and the imaginary, right? So let's just say we have um uh, a what I mean, a complex number here z, and then we have the coordinates x and y. And then this is the angle it makes with the horizontal, right? So let's start with the simpler one first. So right, if so we can see here this is y and then this is x. So if we want to find the argument, right, you can see that tangent theta equals to y over x. So theta, right, is actually just arctangent of y over x. Oh yeah, arctangent just means tangent inverse. It just means that they just mean the same thing. So yeah, it's just arctangent of y over x. So that's how we get our argument actually. So likewise, right? If we want an argument like here, right? Let's just say this is A and B, right? So what we need to realize is that this distance is B and then this distance is A. Then like let's just say this is called alpha. So tangent alpha equals to B over A. Alpha is arctangent B over A. So what I do is I like to find the magnitude of the angle first because I don't want to care about the sign. The sign can get really confusing, especially when it comes to like finding the arguments of really complex like complex number functions. So what we want to do is I personally like to find the magnitude of the angle first, then I try to see what the actual argument is. So right now that we understand how to find the magnitude, now let's consider the positive and negative signs of like arguments. So usually in 99.9% of questions that I see, right, let's just say we have let's see what form do we want to use. Maybe let's use the polar form REI theta, right? Usually this theta, right? If y'all notice, right, questions, right, actually, right, they always define theta, right, to be between positive pi and minus pi. So your theta, right, has to be within negative pi and pi. So the moment is not within pi and negative pi, you have to do this thing called like scaling by a certain factor. So yeah, essentially your argument has to be defined within these regions unless stated. So what do I mean by positive pi and negative pi? So you can think of a way as like some intuition, right? It's like positive pi is like here, positive pi, and negative pi is here. Because you see, right, if let's say your complex number is here, right? Even though you start from here, right? There's like an easier way to go from here to here instead. So we do here, just that we change the sign to be negative. So it's like we're traveling from, oh yeah, pi is inclusive, yeah, my bad. Is pi inclusive? I think pi is inclusive. I still don't have, yeah, I think pi is inclusive. So yeah, thanks for the reminder. So it's just that it's like we're going this direction instead. You know, it's like instead of going here, we go the shorter way here. So that's how I like to think of arguments itself, right? So there's a kind of like a rule of thumb in trying to find the arguments. Not like a rule of thumb. So which is why I say this goes back to your Sec 3 A maths, right? So oh really negative pi isn't. Look, I'm looking at the comments right now. I didn't know negative pi isn't, my bad. Um I mean yeah, that makes sense. So correct. So I might be wrong on this lah, but theta is usually defined between negative pi and pi. So it's inclusive of pi, but it's not inclusive of negative pi. So yeah, I didn't know that, my bad. So at least now I know. Okay, so um I think I'm not sure whether you all remember, but in like A maths, we learn about principal values and all like principal values of like angle. So let's just say remember like um so we go back to what we remember, what we recall, and see how we can apply this understanding and this intuition that we already formed earlier when we studied math at like the simpler levels, right? So remember when we have like sine theta equals to half, right? Sine theta equals to half, right? We take, I'm not sure whether you all use alpha, right? But at least what I learned is that alpha is like the principal, I think it's called principal angle, is it? I can't remember already. But like, so we take sine inverse half, which is pi over 6. Which is pi over 6. So this is our thing. So remember the first quadrant, right? It's like how first quadrant is alpha, pi minus alpha, uh, pi plus alpha. Then we have 2 pi minus alpha. Remember this? Remember this? It's like sine, then like theta can be like pi minus pi over 6 or pi over 6 dot dot dot, right? Depending on what the thing is, right? So we apply this understanding and this intuition that we formed into complex numbers. Of course, the rules are not the same lah, but they are similar. So let us now see the similarity between our Sec 3 A maths, right? Or Sec 4 A maths, I really cannot remember, into our complex numbers. So complex numbers is quite interesting actually, because it really it actually comes from a lot of uh intuitions that we learn as we learn mathematics growing up lah. So let's just say we have complex number that is here. It's denoted by z. So this one argument is just theta lah, nothing much to talk about lah. So argument of z is simply theta. Let's just say we have a complex number w, and then like we define this is the principal angle. Let's just say, because like it's like we don't, I'm sure you remember, right, when we want to like in the second quadrant, right, because we don't want to find, it's hard to find this angle, right? This is called beta, right? So we find this angle alpha, and then we take 180 minus alpha to get beta. So argument of w right here, right, is actually pi minus alpha. So how I like to see is that it's like, it's like pi minus alpha. So it's like we're going pi and then we're minusing alpha. So, and then let's say we have a one in the third quadrant here. Let's just call it z prime because I'm running out of ideas on what to call it. This one, right, is negative pi plus, let's just call this angle, so I cannot think of any more, but let's just call this gamma, right? So it's like this argument of z prime here is minus pi plus gamma. And then the last one here, let's just call it w prime, is simply just, let's just call this sigma, right? So it's just argument of w prime is just minus sigma. Okay, so you can see that it's a bit confusing, right? And I do admit, I don't actually memorize this. So let me show you how I actually do it. And I think it might help you guys, but that's like how one actually does it, like methodologically lah, if I pronounce that correctly. How I like to do it is that first thing I remember is that theta has to be between this value. So let's just say, right, if I have a complex number in the second quadrant, right, let's just call it z. What I do is I find this angle alpha, and then what I remember is that arguments always start from here and goes to here. So I know that the argument of z is beta, but how do I find beta? I cannot find beta directly, but I can find alpha directly. So what I do is I find alpha first, then I take pi minus alpha. So you see, I intuitively understand it without memorizing any formulas. And likewise, right here, right? Let's just say we have w here, right? And then like, remember again, right? Because it has to be within these values, right? I need to find this angle because it always starts from the real positive real axis. So I'm looking for, right, is this angle, let's just say sigma. But I can't find this angle directly. So likewise, I find this angle alpha. And then in this case, right, what I do is I do minus pi plus alpha because I want to get to here. So minus pi plus alpha. So that's how I see it personally. So I hope that kind of helps with simplifying like the amount of memory work that you need in mathematics because it can get confusing at times. So yeah, now that we understand arguments better, right, geometrically, how does it work, right? Now let's look at some properties of arguments and yeah, let's look at some properties of arguments and modulus. And after that, right, we're actually ready to go already. So the first property, honestly, I don't remember this, but now that I look at it, it's good for me to revise. Argument of z1, z2. Okay, never mind. So arguments work similar to logarithms. I think y'all will have noticed this already. Arguments work the same as logarithms. Okay, I have 8 minutes left, so if I cannot finish this 8 minutes, I will just set up another meeting lah. So, but I think I can finish it fast enough. So arguments work the same as logarithms. So that's the intuition that we have. So argument of z1, z2 equals to argument of z1 plus argument of z2. So this is similar to log. So let's just use log base 10 lah, whatever, right? So like x, y equals log x plus log y. Log x plus log y. Same thing, right? The intuition comes from here. So likewise, argument of z1 over z2 is argument z1 minus argument z2. So that's how we do it. So rule of thumb works the same as logarithms. Next, so remember argument of z to the power n, you can bring down the power n argument of z. Just like how we have log x to the power of n is n log x. Same thing here. So you really see it's very intuitive once we understand the links between logarithms and arguments. Seriously, it's very, very intuitive and it's quite fun actually. So the last one, right, that is special to arguments is that, so let's just say, right, oh yeah, I forgot to define. So if we have z equal x plus iy, right, z conjugate, we denote it by a star here, equals to x minus iy. So how about is a conjugate? So let's just say we have z equal x, y. Z conjugate is x and minus y. So it's just that, so z conjugate is the reflection of z about the real axis, you can see here. So that's how I like to see it intuitively. So it's like a reflection like that. It's like we're flipping, we're scaling, we're just flipping the y to become a negative y. So right, argument of z conjugate, right, is actually just negative argument of z. You can see here, right? Argument of z prime is, let's just say this is theta and this is alpha. Since the magnitudes are the same, they only differ in terms of where they're positioned, right? We can say that argument of alpha, sorry, we can say that alpha equals to theta. We can safely say that because the angle that they make the horizontal is the same. You can prove it, it's not that hard to prove it. So, but the difference is that it's the direction that kind of like differs. So argument of z conjugate is actually equals to um theta, right? Theta, which is actually equal to negative alpha. And what is alpha? Alpha is equal to argument of z, negative argument of z. So this is how we see the relationship between the conjugates itself. So if I go too fast, y'all can like watch again. So yeah, y'all can like just give me a text if you like don't really understand it. So let's see if there's anything else that I want to go through. Maybe let's go through some properties of modulus. So let's just say we have modulus z1 and z2 is distributive. So it's equal to modulus z1 plus modulus z2. Same thing if we have modulus z1 over z2, modulus z1 over modulus z2. Z to the power of n equals to mod z power n. So this one like no choice, I just have to memorize. And then the last one, the one that always likes to trick people, right? Seriously, I've seen so many questions that try to trick people. It's quite funny. Modulus of z conjugate is actually just modulus of z because I've already explained how they only differ in terms of the arguments that they make, but the coordinates, the magnitude of the coordinates are the same. So yeah. So I think that's really like about it for complex numbers. There's just maybe one more thing that I'd like to go through. So conjugate root theorem. So conjugate root theorem. If let's just say, right, we have something like az squared plus bz plus c, whereby a, b, and c are real coefficients, right? Let's just say that the solution, one of the solutions is z equal x plus iy. Because the coefficients are real, we can safely say that its conjugate is also another root. So what I like to do is there's nothing really much to understand. It's more like a memory kind of work. So there's some things that we have to memorize, but there's some things that we can kind of understand. So the closest thing that I can kind of try to explain is that, you know how like roots really come in pairs. So it's the same idea here. Roots come in pairs. So it's like, you know the quadratic formula b squared minus 4ac, right? We have a plus minus square root here. So I would guess that if the coefficients here are real, these two are the conjugates exist. So I mean, sorry, the pair conjugates are part of the solutions. So this is like the plus version of the square root, and this is the minus version of the square root. So yeah, if we want to solve complex number questions, this is how like we will do it lah. If not, there's really nothing else to talk about lah. Honestly, we've really explained most of what we need to explain really complex numbers. So actually we can start doing questions already. So actually why don't I'm gonna like stop the lesson here for now. So the next lesson, right, we'll be going through some questions that are really, really very important, and like the question types for complex numbers, because they're really very fixed. The kind of question types that come out are seriously like they're quite similar. So you can kind of like prepare for the kinds of questions that will come out in complex numbers lah. So yeah, I hope this has helped. And yeah, so see you all in the next lesson. We'll be going through some interesting questions uh that we will try together lah, right? So we'll do some basic, then we'll do some more advanced questions. So yeah, thanks for coming on today. I hope this has helped, and see you at the next lesson. Goodbye.